Okay, so go on, please.
Yeah. So the main result of this paper is showing how contraction theory can be used to unify and generalize a number of results in literature. There's a number of results about showing how on stoichiometric compatibility classes, there's one unique equilibria that all the trajectories converge to, and there are various methods to show this. And we show how contraction theory can capture a number of these different results and kind of put them together. So that's the main thing, contraction theory to show kind of global convergence to unique equilibria. And here I have a couple examples of different reaction networks that fall under this theorem. And for the first couple slides, I'm going to be talking about reversible networks, but towards the end, I'll note how this extends to irreversible networks as well. So now, so first I'm going to now go over a bit of just background. So what is a reaction network? It consists of species, complexes, and reactions. Species are like the different parts that come together. Complexes are describe sets of how things come together, and the reactions describe rules between complexes going to other complexes. So an example here, a simple reversible reaction, A plus B back and forth C. Here species are A, B, C. Complexes are the set AB on the left side, the set C on the right side. And on top of the reaction, we have a reaction rate that describes how fast the reaction proceeds. In this case, I give an example of mass action kinetics of a reaction rate. I also note in general for reversible reactions, I'll say the left-hand side are the reactants and the right-hand side are the products. And for reversible reactions, I can kind of just choose orientation. If you flip the reaction, you get the same thing. But yeah, this is the orientation we'll choose. Left side is reactants, right side is products. Now I'm going to talk a second about the stoichiometric matrix we can associate to our reaction.
ते नाही, ते गुड नाईटचं फक्त हे आहे त्यांच्याकडे, ते नाही, that's not, ते नाही.
Oh, Abhishek, was that a question or is your, oh, okay.
Yeah, sorry.
Yeah, I'll get that. Network, we can associate stoichiometric matrix, and this is just associating numbers to the reactions. So in general, for the reaction networks I'm going to consider, they're going to be not catalytic. So if a species appears on one side of the reaction, it does not appear on the other. And this is going to be convenient for defining the stoichiometric matrix. So the stoichiometric matrix is going to be a matrix where each column refers to a reaction vector and each row corresponds to a species. So in general, we have a formula for computing each entry. And as an example, take the second column of the stoichiometric matrix we have here. The top right is just essentially, we have 2A going back and forth B. It corresponds to the term in front of A. So it's 2A. The reactants get negative coefficients, and so we have a -2 here. And then the second row corresponds to B, and we have a 1 coefficient in front of B, so we get a 1 here. So this stoichiometric matrix is kind of just a matrix that keeps track of the reaction network. Each column gives the numbers that correspond to the stoichiometric coefficients in the reaction. Yeah, and as I mentioned before, non-catalytic species, not both a product and reactant. Our results only apply to not catalytic reactions. And then, so finally, we have a stoichiometric matrix. We talked a bit about reaction kinetics. So our result is about dynamical systems. Actual dynamics is going to be able to form x dot equals gamma r of x. So stoichiometric matrix times the reaction rates. And again, going back to our example, A plus B back for C and 2A back for B. We can write our right-hand side in this form, stoichiometric matrix times reaction rates. And if our reaction rates are mass action kinetics, we have a little bit more information. Yeah. So R of X is the reaction rate columns, and I note that each entry in this column is defined on the non-negative orthant because species have to be, you can't have a negative amount of stuff. And yeah, and I know sometimes I refer to the system as, I use gamma to identify the system, abusive notation, just because gamma for non-catalytic reactions, it's unambiguous what each reaction will be if they're not catalytic. Another term, so I'll refer to the image of gamma as a stoichiometric subspace. So that kind of describes all the directions the reactions can go as we choose different kinetics. And yeah, as I mentioned earlier, we sometimes refer to the columns of gamma as the reactions, just kind of going back and forth. So the assumptions are all right. So I mentioned mass action kinetics, but the assumptions we use in this paper is more general. So first assumption, RIs are continuously differentiable. We have some positivity, negativity conditions. So if none of the products are present, the reaction can only move kind of forward from reactants to products. That's again related to you can't have negative stuff. If a product is not present, you can't push it to having negative product. And then a very important condition, signs on the partial derivatives. So if XJ is a reactant, and we increase reactants, the reaction will have an inclination to produce more products. And if we have increased the products, we'll have an inclination to go back to the reactants. And if the species is not involved in the reaction, it doesn't impact the kinetics. And then one other condition, that in some cases this derivative is a strict inequality. So if every reactant is present and we increase reactants, we're definitely going to increase going towards the products and vice versa. Okay, so that was a little bit about reaction networks. And now a little bit about contractivity. So we're going to use the term weak contractivity. So suppose we have a space, a norm in the space. Weak contractivity just means take two trajectories. That distance between them is going to be strictly decreasing in time. They're not necessarily exponentially going towards each other, but strictly decreasing. And a nice thing about this is if we have a compact convex space we're evolving on, we have a fixed point by Brouwer's fixed point theorem, and then everything will have to converge to this fixed point. So nice convergence properties once we have weak contractivity. One other term I'll use is non-expansivity, and that just means the distance is not increasing. Not necessarily decreasing, but just not increasing. Now I'll talk for a minute about monotonicity. So first consider a closed convex pointed cone with non-empty interior. And recall pointed means if you have a vector in the cone, x, then minus x is not in the cone. So we say we're monotone with respect to this cone K if initially we have 2 points and the difference vector between the 2 points is in the cone. Then as these evolve, this difference vector stays in the cone. And one can check that given the condition of the cone, this is in fact a partial ordering. So the system kind of preserves a partial ordering as it evolves. And one other important condition, strong monotonicity. So monotonicity is just preserving the partial ordering. Strong monotonicity means this vector is initially on the boundary of the cone. Then in arbitrary small time, it gets pushed to the interior of the cone. So things are kind of getting pushed off of the boundaries of the cone. And I'll skip over the details, but this can be naturally applied to, if some affine state space. So our reaction networks generally evolve on it's kind of a foliation of the non-negative orthant. And it's natural to extend this. We just have a cone kind of the same dimension as these subspaces or affine spaces. Okay, so now I'll state the main theorem. So a few terms used in the main theorem. So first, let S be the set of matrices with each entry -1, 0, or 1, and at most 2 entries in each column. So these are going to refer to some kinds of reaction networks. So they essentially look like A back and forth B, B back and forth C, maybe A plus B back and forth empty set. And these, yeah, essentially things going back and forth into other things. ST is just kind of the dual of these, just transpose the stoichiometric matrix. Let N be the union of all these guys. P will be a set of matrices where each row has the most 1 non-zero entry, and no column of zeros. D will have non-zero, just diagonal of real entries. This matrix P essentially will refer to sometimes species always show up together, and we can kind of treat them as one species. That's what's PLP. And D is essentially saying you multiply a reversible network by like 2, you get the same class of dynamics.
Excuse me, Alan.
Yep.
So
Yep.
If the stoichiometric matrix belongs to S, then it doesn't mean that it is a first order reaction. It may mean that 2x goes to 3x, for example, because then again, 1 is the difference.
If it belongs to
2x.
Oh, sorry. No twos. It would be like 1x goes back and forth 1y. There would be no 2, no 3. If I can
As is the
draw.
stoichiometric, it contains the differences of the stoichiometric coefficients.
But also there is no catalysis, so you cannot get that.
Oh, I see. You are right. Thank you. So then you can only have first order reactions.
I also assume general kinetics. So, it's not necessarily a linear dependence. And also with this matrix P. Sorry, let me go forward. So here's the main theorem. It's possible to have.
Wait, may I just because I think I see what the question is. So they're not really first order reactions, right? Because you can take, I don't know, A plus B goes into C, right? That's a second order reaction. What you cannot have is 2 molecules of the same type. So you can't have 2A plus B goes into C. Is that correct, Alon? Did I say
Yeah,
right?
that's true. There are networks that involve A plus B back or C. True.
Right. So the point I'm making is that first order reactions, the way I understand it, the way I think everybody understands it, means that everything will be linear, that there will be only one -1 in each column, but that would be too restrictive, but that's not the restriction. But however, the fact that you don't allow 2 molecules of the same type is a little bit restrictive, I guess. But that's
if A plus B goes to C, then we have 2 -1s and 1 +1. So we have more than 2 non-zero entries.
So maybe just A plus B goes to 0.
True. Yeah, so A plus B goes to 0 would be valid. Also, so there's no catalytic reactions, and also in this set S, there's no 2 entries, but there are reaction networks with the 2 coefficients in our main class here. There are reaction networks with 2, 3, 4 n coefficient.
right. Right. So the matrix in the middle has some constraints, but you still are allowed this P and D matrices, right?
Sure.
Right. Maybe you can show an example later if you have a chance of how you could decompose a matrix, like, how you can get A plus B goes into C in that format, right? And
Yes, but I think, Janos, is also that you allow S transposed as well. So then you can have 3 things on a column because the columns becomes rows.
True. Yeah. So I'll also have a few examples of this later, but yeah, it's not necessarily first order. You can have arbitrary order reactions. But I will say these are, special looking reaction. They're essentially things that go back and forth, A back and forth B, B back and forth C, A plus B back and forth 0, and the dual of these. That's essentially how I think a lot of these reactions look. Although with this P and D matrix, we can end up having higher order terms. We can have 2, 3, 4, 5, etc.
Yeah, I think when you show an example, it'll be more clear to people.
Okay, yeah. After about, I think, 2 or 3 slides, I'll have some examples. Or yeah, okay, I'll go back to these. Yeah, here are a couple of examples of this reaction, some reaction networks that can work.
Right, yeah, I think you should, yeah, later you should, yeah. But there was a great question.
But yeah, so in the matrix S, each column has at most 2 entries, 2 non-zero entries. The transpose is such that each row has at most 2 non-zero, and that's essentially saying each species appears at most twice in the transpose. And so example 1 is an example of this, where we do have 3 entries on the left side, but each row has at most 2 entries. Example 2 shows an example of the P matrix. So A and B kind of always show up together. So we can kind of treat them like one unit. And then we get this kind of simplified matrix on the right here.
In the first example, I don't see the place for F. Here we have 6 species and only
1, 2, 3,
5
4.
rows.
1, 2, 3, 4, 5, 3, 4, 5, 6. You're right. This is a typo.
Okay.
Yeah.
Not important.
But yeah, F appears only 1 time, so it would work out. So yeah, the main quality being that in this reaction network, each species only appears most 2 times. And yeah, so these are a couple examples. And then I'll go back here. So I also want to make a remark on non-expansivity and monotonicity. So in this paper, we kind of go back between these 2 conditions, non-expansive, monotone. In the context of this problem, you can essentially do both at the same time with no problem. So we're going to use monotonicity conditions and essentially consider non-expansivity as a special case of it. And so very roughly speaking, we're going to for a non-expansive system, we'll think of lifting the system. Essentially, we're just adding a dummy dimension. A dimension, we have a dynamical system, depends on some variables. We just add an extra dimension that doesn't impact anything. So imagine like a system like x dot equals x, y dot equals y. And then we just add a dummy thing, z dot equals 0. And this is a little bit, this is very simple little trick, but it allows us to kind of bring in monotonicity conditions. Just doing this trick, there are some necessary and sufficient conditions to be monotone, and you can just apply them pretty directly to being non-expansive. And then for the reaction network, the lift is essentially adding a species that doesn't show up in any reaction. So that's kind of the dummy species that doesn't actually impact anything. So a bit more information about this lifted system with a dummy dimension. So assume, we have in this picture, we have some system in R2 that's non-expansive. Take a ball of unit norm, so x norm less than equal to 1. Lift this ball up to 1 unit in the dummy dimension, and then find the cone generated by that ball. This system with the extra dimension will be monotone with respect to this cone. And then if we're monotone with respect to a cone, in this dummy system, equivalently, the original system will be non-expansive for a cross section. Sometimes we'll find that we'll have a lifted system that, in the previous pictures, the cone was symmetric. Sometimes we'll find a cone that's not symmetric, but this won't be an issue. We can essentially just symmetrize the cross-section of the cone. If the cross-section is a triangle, we'll just take the difference set of this triangle and get a hexagon, which is a symmetric, will be a symmetric figure. a little picture of us doing exactly that. Examples. Now I'm going to talk a little bit about computational procedure for just building these things, which is very handy for actually finding these figures that work. So first, a couple of terms. So this is going to be a notation for the ith coordinate of some arbitrary vector v. A couple of regions. So Q1v. This will be given a vector v. It's the set of vectors whose signs don't disagree with v. So if v is positive in the first coordinate, they're non-negative in the first coordinate. Q1 plus is a subset of this Q1v. It's a set such that at least one of the coordinates strictly like agrees with the sign. So if there might be one positive entry for v, and then a member of Q1 plus would be a vector with also a strictly positive entry. So a few examples of this. So say v is -1, 1, 0. Q1v will be the non-negative, non-positive, non-negative, and then anything in the last entry. And then an example of a vector in Q1 plus v is will be -1, 0, 0, just because the -1 vector strictly agrees with -1 from v, and so it's in Q1 plus. And 0, 0, 1 would not be in Q1 plus because it's not strictly agreeing with any of the non-zero coordinates. And there's one other entry, Q2v, which is essentially it's just 0 and all the entries are non-zero for v. One other term, extreme vectors of a cone, is just vectors not a strict combination of any other vector. So we have a polyhedral cone, they're just kind of the farthest out, the vector sticking the furthest out. So this lemma is essentially underlies a way you can compute the norm balls. It gives a sufficient condition to be non-expansive for a figure. And essentially, if you take a vector in the polyhedral ball that's an extreme point, and if it's in the positive region for a reaction network, you subtract off a reaction vector, you subtract that reaction vector off, you get a new point. And then you check if that point's still inside the ball. And if it's a negative, you add the vector. And if the ball is closed under these operations, you produce this new vector still in the ball. You will be non-expansive for this ball. And so this kind of outlines a way to actually produce the balls by just starting with a vector and then producing these different points. So show a vector, you just subtract off or add depending on where the region is in, and just keep building up the ball until it's closed. Or it's like you can also show if it grows too much, it won't exist. Whether important note, one can prove that this ball B will be of the appropriate dimension. So when we grow the ball, it should have the same dimension as the stoichiometric subspace that it'll be on. And do a remark on going back and forth between non-expansivity and monotonicity. This also works for finding a monotone cone. As it's closed under these operations, the lift of the ball will be monotone with respect to that. And yeah, going back to the remark, sometimes the ball is not symmetric, or the lift is cone, and then we can just symmetrize and get a figure that is symmetric and will work. And we're going to want weak contractivity instead of non-expansivity. We're going to do that by checking a strong monotonicity condition. And if the lifted cone is strongly monotone, once we symmetrize, we'll get a weakly contractive figure. And note that all of this, when we find the norm, we're essentially finding the geometric figure that's, the ball of unit norm. So yeah, we're essentially finding that shape. And then we can use this formula here, which is essentially Minkowski functionals as a way to go from this figure to a norm. So now I'll show an example of actually computing a ball. So say we have this reaction network, A back and forth B, B back and forth C, A and C. So this is part of the set S, where each reaction has the most two species. So we'll start with a vector 1, 0, 0. Choosing the initial vector for the norms or slightly arbitrary. This is chosen, it works out very nicely, but other vectors would also work. And so we carry out the computation. So for this first vector, this is the reaction vector of A back and forth B. So A is reactance, so -1, B product, so +1, right? And then 1, 0, 0, it's in the Q1 minus for this reaction vector. So we're going to add it because it's in the negative region. We add the vector, and we'll get 0, 1, 0. And then when we look at another reaction, our other reaction vectors, we'll see for B back and forth C, it's again in the minus region, so we'll add it. And we just keep doing this. If it's in the minus, we add. If it's the plus, we subtract. And we'll get out these 6 coordinates. So then you can check or will be closed under these operations. So we do them again, we'll just get back something inside their convex hull. And so we have the vertices of an octahedron, which is just the unit norm ball for an L1. So this system is non-expansive for an L1 norm. So I mentioned strong monotonicity and weak contractivity, which we really want. It takes a little bit more work. So we have a technical lemma here that lets us that we can check to show weak contractivity or strong monotonicity. The intuition behind this lemma is essentially if you have a cone has some face, you can find a reaction vector that pushes you off of the face. There's some technical details, but that's the intuition, just a reaction vector that will point kind of off of it. So I alluded to this a little bit earlier. So going back to the main theorem and the networks P and D. So to prove the main theorem, we're really just going to explicitly find the norms for all the different cases. So first about the matrix P, which is just each entry has the most one non-zero. Each row has the most one non-zero entry. It'll end up looking like a bunch of disjoint columns, and it's just keeping track of species that always show up together, like the A plus B from earlier. And one can show if the reaction network N is monotone for some cone K, then Pn will be monotone for Pk. So this will let us we'll just look at the matrix ND and ignore P, because if we can find something for ND, we can find something for PND that we're monotone for. And as I mentioned earlier, multiplying matrix D does not impact these reversible reaction networks. So we can multiply the reaction networks by 2, and because we assume these very general kinetics, it won't impact the class of dynamics. So these simplifications, just so we can just look at the matrix N for the time being and find the norms that work for that. And so as I mentioned, now we're going to look at the matrices N, and we're just going to find norms that we can prove always work. And then our computational procedure is as a convenient way of finding these norms, finding examples, and finding the general structures that will work. Okay, so what are the explicit norms? So we had S and S transpose. So the class where each column has the most 2 non-zero entries. There are 2 possible figures. And they're both going to be, we describe them both as a set difference, C minus C, where C is either a simplex or a cross polytope. So for the class S, one of these 2 norms will work. They'll be weakly contracted for one of these 2. If C is a cross polytope, that's just a L1 norm, the set difference, possibly up to some scaling factor. And if C is a simplex, like if it's a triangle, you get a hexagon. If it's larger, I think it has 2 n choose 2 vertices. And one can check these figures will work. And then the transpose, we essentially get kind of dual figures. If the columns are linearly independent and transposed, we can check that cube, some kind of cube will work. The columns are dependent, then it looks a little bit funkier. As a vertices, you can take all possible sums of reaction vectors. So you have a sequence of column vectors, the reaction vectors, just for each one, include it or don't include it in a sum, and take all possible choices of it. That figure will also turn out to work. And so these are all the cases. So essentially, yeah, it's cross polytope or difference of the simplex and kind of the dual of these, cube and this other kind of figure. So now I mentioned this previously, I was just talking about reversible reactions. You can generalize to irreversible reactions using the same techniques. So here, just our notation, when we add the reactions, we'll always have, reactants on the left, products on the right, arrow going from reactants to products. So unlike reversible reactions, we don't want to flip them, or this will be our orientation we'll choose. The kinetics are going to be slightly different just to reflect that if we change the products, they won't impact the reaction rates this time. So again, the reaction rates are continuously differentiable. If any of the reactants are missing, reaction rate is reaction does not proceed. In general, if we increase the reactants, the rate will not decrease. And then if it's not reactant, like if it's not involved or it's a product, it doesn't impact the reaction rates. And if they're all present, we have a strict inequality. On increased reactants, the reaction rate will increase.
Excuse me, Alan. I don't see what happens if you have A goes to B goes to C. Then B is both product and reactant. What happens?
I guess that case I would consider that two separate reactions. So yeah, A goes back and forth, it goes to B, B goes to C. So I guess for this slide, I would just, for the reaction A, B, it satisfies these assumptions. For the reaction B to C, it also satisfies these assumptions. So each one of those would have a separate reaction rate.
Okay.
So I'll define a notion of an R graph, and this is R for reaction. The nodes will be reactions of our reaction network. And then we have an arrow from a node to a node, so from a reaction to a reaction. So if VI is one reaction, VJ is another. We have a node from VI to VJ. If VI can impact the kinetics of VJ. So I have here in the more, be a little bit more precise. If any species in VI is either a product or reactant, if VJ is reversible, or is a reactant of VJ if it's irreversible. And the idea being, as VI, changes the amount of species, this impacts the kinetics of VJ. And then we recall here that graph is strongly connected if there's always a path from any two nodes A and B, a directed path, following the arrows. And so with two additional assumptions that this R graph is strongly connected and that the matrix C has positive entries, we can still apply our previous theorem. So to be more precise, if we have a reaction network with possibly irreversible reactions, that can be factored as P and D again, where D is positive, has a positive diagonal, and the R graph is strongly connected, then we're still weakly contracted. And two questions. One thing I'm interested in that I guess I don't know of any reversible networks under these general kinetics that are non-expansive that are not in the main theorem. Yeah, I don't know of any other non-expansive reversible networks under general kinetics. And then one other thing that'd be interesting for this, it takes a bit more work to check strong monotonicity and weak contractivity, to get that. It'd be interesting if we just have non-expansivity, what does it mean for the omega limit sets? Do they still approach equilibrium? For polyhedral norms, seems like it might be true, but I don't know. For C1 vector fields, I don't believe there's a proof of that. Okay, and yeah, this is my last slide. Thank you for listening.
Thank you very much, Joe.